can get the materials from the bit.ly link. And it would help if you have a Google account because we're doing some hands-on with the Google Colab later. Right, so today's topic will be on arrays and stacks, and implement the solutions with Python, which you have learned if you joined us earlier. So I'm Melvin, and Juliana is with us in the Zoom session, and we're from LCCL Coding Academy. Due to the lack of time, we will not explain too much about it. You can find us online and all that. All right, so to get you started, we're going to have a poll. Oh, and then now you can see a black screen. Okay, sorry about that. Yeah, so if you could please respond to our first poll. All right, looks like the poll is done. Unfortunately, I'm sorry, I apologize for a black area on the screen. That's just me looking at the poll. So it seems like most people did not attend our session, but that's okay. They're meant to be standalone sessions anyway. All right, closing the poll. We have a second poll just to find out at what level of a Python developer or programmer you are. So please respond to our second poll. So this will help us to customize our presentation in the following 1 hour. All right, looks like the poll is done, and thank you for responding. About 72% of you have some exposure to Python, and that's like the majority of attendees today. Okay, moving on. All right, so the first topic we're going to cover is arrays. And if you're using Python, we actually don't really hear of arrays that much. What we hear of is lists, right? So we can write a list in square brackets and so on. But if you look at the actual way lists are implemented, in particular in CPython is the standard Python interpreter. They are implemented with arrays, and arrays are essentially a contiguous section of memory, right? So everything we create, all these data structures, they are stored in memory, right? Usually that's the RAM. So here we're creating a list in Python, and beneath that in CPython it's allocated an array of size, in this case, 1, 2, 3, 4, 5, 6, 7, 8 elements, right? Then there's a variable also allocated that references the array. So the key features of arrays is that it is really efficient for us to access any particular index of the array. Say we want the 5th element at index position 5 or element index position 7. Right? This is done in what we call constant time, right? It doesn't depend on the size of the array. We'll see more of that later on as we go through. So why is that fast? How can we do this very quick access? So I think the analogy here is we think of it as maybe like houses along a street, and all the houses are the same size, right? So if we want to find like the 5th house along a street, we don't have to kind of walk down one by one. We can sort of calculate, right? Because we know the size of every house and where is the beginning of the street of houses. We can just multiply by all the intervening houses, and we can get to the one we want immediately, right? We get to the, let's say, the GPS position of the house. We can just calculate it immediately and know where it is. So it's the same for arrays, right? So we can do some arithmetic and looking at the start position and looking at how the size of every element, we can sort of get access to the memory address of the ith element with just a few calculations. Okay, so we're going to do some hands-on activity right now. And this is where the Google Colab will come in. We're going to compare an operation, which is pop. The pop operation is provided by the list class. And we're going to compare 3 different cases, right? Popping items from the back, popping items from the front, and popping items from the middle, and for different sizes of lists. So if you go to the shared folder, you would see something like this. There'll be 2 files. There'll be a IPython file, IPYD, I think, and then there's the presentation slides. So yeah, so if you look at the file called LCCL array experiments, here is shown this the left-hand side. And if you click that file or double-click that file, you would see a screen like this. And then if you go to click on, if you have not used Colab before, then you can click on Connect More Apps, and then search for an app called the Colaboratory. This is, I think, a first-party app from Google. So if you click on that app, you can then install it. It doesn't really download anything. I think this is just installing it to your Google sort of account. And this is like an online kind of IDE, basically. So if you click install, this will install it into your Google account. And then if you go back to the LCCL array experiments IPython file, then now you can see this open with Google Colaboratory. So if you select that, this IDE will load, and it is recommended that you first save a copy so that you can easily modify things and so on. So save a copy, select file, and save a copy in Drive. And then you can make modifications and run it. So let me try to do a little demo, I guess. So I have it open here. I double click the file. This is the shared folder. Whoops. Okay, I mean, that's fine. Here it actually shows the content, but it doesn't matter. Open with Google Colaboratory. Click on that. It opens a new window, which is the Google Colaboratory. Takes a second. I think I have this dark mode enabled, but similar. Go to File, click Save a copy in Drive. Right, and then you just save and then open another window. We can close the original one. So it will say copy of LCCL array experiments and so on. Because I think you can't modify the original one because that's the original file. But you can modify the one that's your own personal copy. So just to briefly explain what we have here, we have some setup which creates an array of a particular size, all zeros. And we have a code which is going to be timed, right? So code, in this case, is going to pop from the back. Pop from the front, actually. Pop 0 means pop from the front, right? Pop 0 means remove the first element at position 0. Right? Pop from the back would be just pop. So here, and after that, we have a small snippet of code that calls repeat. Repeat is a function from the timeit module, which will run this fragment, in this case, 100 times. Yeah, and then measure, it gives you a list of 100 elements, representing how long it took for the code, which is this a.pop0 to execute. So in this case, I have previously ran it. And we take the minimum, just to eliminate any other noise factors from the running time. So if you click on it, it will run, and then it will output a number showing the minimum time it took out of these 100 trials. So this is for popping from the front for 1,000 elements. Okay, so if we go back to the slides, if you could take the next 2 minutes to try removing from the back, which is just calling pop, removing from the middle, you have to use n/2. And for lists of the various sizes, 10, 100,000, and 10,000, and then sort of maybe create a separate table somewhere to record down your readings. Okay, please proceed, and then we'll take 2 minutes to work on this hands-on. Okay, I think time's up. That's a really long 2 minutes for me. So hopefully you've managed to try at least a couple of different sizes of lists and the different operations, right? Popping from the front, the back, and from the middle. So we have done this before, and yes, tabulation of our results. We did a couple more values so that we have a smoother curve to show you. So here on the x-axis is the size of the list, essentially, the n, and on the y-axis is the time in e to the -7 seconds, which is really fast actually. So the key thing here, if you look at it, is that the blue line, which is popping from the back, which you're just calling pop with no arguments, is pretty much flat, right? And if you look at even the numbers itself in the table, it's like 4, 5, 11, 14. It does get slightly longer as the list get more, but essentially it is flat, right? Even if you increase the list from 10 to like a million, the number doesn't really grow that much. So it's practically flat, as you can see from the graph. The other ones show a very clear linear trend, right? I mean, front is actually the slowest because it's the highest line, and middle is somewhere in between the two. So in this workshop in particular, we'll be quite interested in which operations are fast, which operations are slow, and all that. So here we want to understand like why does this occur? And it really comes back to our notion of an array being this contiguous section of values. So here is an illustration of moving from the back, right? Just calling pop. And there's nothing that special to do. So we're removing the number 49. And we just have the array as before, and it's still in one contiguous chunk of values. Now, the different thing happens when you try to move from the front, right, which is pop 0, right, as in what I demo. So when we do that, then the first element is going to be gone. So 23 is gone. But unfortunately, it leaves a hole, right? So from the front of the array to the first element is no longer, just immediately at the front. The first element now is sort of in the second place, and the second element is in the third place, and so on, right? They're all kind of off, right? Because now we have a hole. So the way to resolve this, actually, we need to close up this hole. Right? We need to pretty much move everything one step forward. And that's where the time went. So we're actually adjusting all the elements to move one step forward, so that it's still this contiguous chunk of values. So we can't actually have any gaps, right? So if you think about it, if we have gaps, then we can't really get to the ith element instantaneously, right? Because there are all these gaps in between, and we don't know how many gaps. So we can't really use a calculation to get to the ith, the memory address of the ith value. Yeah. So that's the problem, right? So I mean, for middle, I think we didn't animate it here, but middle you would see it's the same problem. So when you delete from the middle, you pop somewhere in the n/2 position. Again, there'll be this gap or this hole in the middle, and this prevents us from doing the ith element access, right, easily, because it's no longer contiguous. We've made it fragmented, right? Because with all these holes everywhere, it becomes fragmented. So we can't really have this. So this is almost like a compaction. We have to compact everything to the front so that it's contiguous. That's why we can get the efficient access. And because of maintaining this invariant of having everything contiguous, the access is fast, but deletion, especially somewhere near the front, is going to be slow, right? Because we're going to have to deal with moving everything up front to close up the gap or the hole that's produced, right? So that's the array. So there's this trade-off here. For having very fast access, we are trading off somewhat slow removal from near the front, right, because of this requirement to close up any gaps. So if you take other courses next time, you will learn about other data structures that try to address this, this problem. So they will try to trade off the access speed. So they'll say, okay, we'll allow slower access of the ith element, but we'll make removal faster, right? There's always some trade-off, right? There's no free lunch. So in order to make removal faster, actually we got to trade off the access time of the ith element, make that slightly slower, but in order to gain speed in terms of removal. We won't be covering it in this workshop due to lack of time, but you will cover that in, probably in other classes. Okay, so that's pretty much all that we will say about arrays. Arrays are one of the most basic data structures there is. So now moving to a slightly adjacent topic is a different data type called a stack. And the stacks are quite common. I mean, stacks of plates, stacks of books, stacks of papers. I unfortunately have stacks of papers right next to me on my desk. I should really clean it up. A stack is where something you add to the top, and then as you add, it gets taller and taller, right? That's a stack. And then when we remove, we also, of course, we remove from the top because the top is not under a pile of things, right? We can't remove the last one because it's under a big pile of things. So we always also remove from the top. And hopefully you remove everything at some point, we clean up that stack of whatever it is that you have. So these are the two operations, right? Adding to the top and removing from the top. So this is a stack. So here's some visualization. We also call this a last in, first out structure because the last item that goes in is also the first item that goes out. The last piece of paper you put on top is also the first thing that gets taken away, right? It's called last in, first out. And we would still use a list because a list allows us, if we recall just now, a list allows us to operate at the tail of the list, the very back of the list very efficiently. Even removal is fast, right? The pop operation is fast, if you recall. So a list turns out to be a good way for us to model a stack, right? So we would use operations like append. Append would add to the back, which is fast, right? Similarly, if you think about it, append to the middle is also slow for a list, although we didn't quite cover that, but it has the same issue. If you append to the middle, you're going to create a gap and then put the stuff in. But we're appending to the back, so it's fast. So pop, we've seen. So pop removes things from the back. So the back of the list essentially represents the top of the stack, right? And the front of the list is the bottom of the stack. So we'll actually never try to deal with the front because that's slow. We ever only deal with the back, or in this case, the top, right, for a stack. So list is quite appropriate because operations on the back is fast. All right, I think we're going ahead of time. Okay, that's a good thing. Okay, so now we want to do some exercises. Now you know about stacks, but how do we use stacks to solve some actual problems, right? So we're going to look at one particular problem. So I'm going to break out of this for a second and go to, let me just quickly introduce this resource. It's called Catis or Catis. I'm not really sure. But anyway, it's a place where you can get, you can create an account and you can get different kinds of problems. These are sort of programming contest-like problems. I think it's quite similar to what you actually get in the Shopee challenge. So they have different difficulty levels and so forth. So I have selected two problems that we will look at for today. So I'm just going to, let's see, I'm just going to go through the examples maybe. It's a little bit easier. So it's quite intuitive, I think, this problem. So we can avoid looking at all the text. So here are just different example inputs, right? So I think the first character is just the, the size, how many characters coming out next. And the real input is this sequence of different kinds of parentheses, right? You have the curly braces, the square brackets, and so forth. I think you can have even the what is this called? The one we use for set, right? Which is this, I forgot the name of it, but it's another kind of opening brace. So there are essentially three different kinds of braces or delimiters, as is mentioned here, that we will be looking at. So the question is this a well-formed expression, right? Meaning that all the opening braces are closed properly, right? Just like when you have like opening quotes, right? You have to close the quote. They have to balance, right? Otherwise, it's not well-formed, right? Or it doesn't really make sense, right? So if you look at the first example, I think we should also have on the slide, this one doesn't quite make sense, right? Because we open with the parentheses, and then we have two bunches of, the two square brackets are fine, but we close with a right square bracket, right? Which, if you look at this, it's clearly not balanced, right? Or it's not well-formed. So the last symbol should be the parentheses, right? The round brackets. So in this case, we will have to say this is not well formed, and it's not well formed because of this because of the square brackets, the last character. I think in the problem, you have to state where the thing went wrong. So the task is to check if a given sequence of these delimiters, these different kinds of brackets, are properly closed, right? So every opening must have a corresponding close and so forth. Okay. So why a stack? A stack in this case is because when you see a closing parentheses, it actually closes the most recently opened one, right? So there's this last in, first out kind of feeling there, right? Because the next closing parentheses, it should be closing the one that you just saw most recently, not the one very, very early on, right? So we're always closing the one we just saw. We're always closing the opening bracket we just seen. So let's see that in action. So what we would do in this case is we would go over all the characters one by one. So when we see an opening brackets, in this case, round brackets, we push it onto the stack because this is like, okay, this is not yet closed, so it needs to wait for the closing one. So it's kind of waiting for something. So we put it onto the stack to wait. And then we see another, this is the square bracket, the opening square brackets. And it's the same thing, right? So it's also waiting for a closing square bracket to appear, to be balanced, right? So it's still waiting for something. So we again put it into the stack to wait down there. And now in the next character, we see the closing square brackets. And now the question is, who should this be paired up with among those that are waiting? Right? And as I mentioned just now, it's going to be the one that was just got in, right? It's not the one that got in at the beginning, but the one that just entered waiting, which is the one at the top of the stack. So the two highlighted in red are going to match. That means this particular part is done. Right? I mean, these two square brackets are good, right? So we can remove the one that was waiting because it has found its partner, essentially, right? It's found its other closing, the opening and closing have found each other, so they can be removed from the stack because it's no longer waiting for something. And then we proceed in a similar fashion. So again, we find an opening one needs to wait until it sees the closing. So it goes onto the top of the stack. And now we find the closing means, it's found its partner. So it can be removed because it no longer has to wait for the partner. And finally, the last character we see is the closing square bracket, and we try to find its partner, right? Which should be the top thing on the stack. But in this case, when we do this, we find that, oops, we can't find the right partner because the top element on the stack is the wrong kind of bracket, right? It's not the square bracket, it's the round brackets. So that's when we would print an error message, right? But if it was the correct one, then, well, again, it will be removed, right? It means it was no longer waiting, and then the stack would be empty at the very end of going through all the characters. Then we would be perfectly balanced. Means every opening has a corresponding closing. And that's essentially the main idea here for this task. We're trying to have all the opening ones wait in the, let me just run through it again. So they will wait in the stack. And when we have a closing one, we always match to the one that was most recently added to the waiting stack, right? The one on top. So it has this last in, first out concept that we discussed. So when we find the matching, we remove it. And if we find a new one, we have to go in and wait. We find the matching one, we remove it. And we find a closing, we try to check if it's matching. No, that means something went wrong, and we output the position where it went wrong. So that's the sort of the algorithm of it and how we use the stack. Okay, and next we will see how it's implemented in Python. Unfortunately, this is slightly long, and this doesn't include the input-output, right? But this more or less describes what I just mentioned, except we have a small complication. Sometimes there may be spaces. So the input sequence might contain spaces as well as the different kinds of brackets. So that's not too difficult. We just have to handle, in this case, we notice we take care of the spaces right at the beginning, and we just essentially ignore them because the spaces don't participate in the matching of brackets. So we just do a pass, right? So for the first case of a space, we just pass. Otherwise, we have this dictionary called opening. Opening tells us for every corresponding closing bracket, what is the opening pair, right? That should match up with it. So you can see opening defined at the beginning. So next we check if the character is one of the opening or the left-hand side of one of the brackets, right? Opening dot values means these are the actual opening parens or the opening brackets. So as I mentioned, if we see an opening, means it has to see an opening or a left parenthesis, a left bracket, it has to wait for its closing to appear. So it has to go into the stack. Right? So here we do stack dot append. So it goes in the stack to wait. If it falls through to the third case, means it's not a space and it's not an opening, then our conclusion that is it must be actually a closing, because the input statement says the string can only contain 3 kinds of characters: opening, spaces, and closing brackets. So if it goes to the third branch of the aleph, it must be the closing, right? So C must be a closing bracket. And in that case, we have to check a few things. So this is the case where things go wrong, right? So this case, when things go wrong, means there are 2 cases. One is the stack is not, there's nothing in the stack. So that can't be, because normally if things are correct, then I must be able to find my corresponding opening on the top of the stack. So if the stack is empty, then that's also incorrect. It means we have an extra closing bracket, right? But no opening for that one, but extra closing. So that's still wrong. It's not balanced. So otherwise, if it's not empty, that means there must be some character on top. Here we are using stack -1 to sort of look at the element on top. If you recall, -1 is actually the last element in the list, which is also the top element of the stack, right? So here we're checking if opening square bracket C, which is referencing the dictionary, right? So opening square bracket C gives us the actual expected opening symbol for that particular closing symbol. C is the closing symbol. So opening square bracket C gives us the corresponding left-hand side, the left side bracket of that closing character C. So that has to be the same as what's on top of the stack. If it's not the same, like in our example, we expect to see a left square bracket, but we saw instead a left round bracket, right? So this is true, right? So we get this, the second condition, opening C not equals to stack -1 is true. So it's wrong actually, because it should be equal, but in this case it's different. So that means there is an error, right? Exactly what happened just now. So we need to print out the character where it is the error and the position of that character, which is quite simply just the I in the enumerate sequence. That's the whole reason we do enumerate at the very beginning of our for loop, because we have to print out the position as requirement of the question. So here we just print C and I, separated by a space. And if all of this are not true, then it must be the case that the thing on top is what we expect, right? That means the stack is non-empty and there is a character on top that is equal to what we expect to see. Then we just remove the thing on top, because now it has been matched with its corresponding closing. So the opening and closing have matched, so the opening can get out of the stack, right? Because it's been matched. And at the very end, there's this somewhat unusual structure, right? We have an else. Why is that else? But there's no if. Actually, there's this little secret in Python that for loops can also have an else. And that happens when you exit the loop normally, right? So if you exit the loop normally, not through any break or any special condition, then the else part of the for loop would execute. So if we go through the whole sequence and everything occurs properly, and we never encounter the third case where we do a break, then we would actually print okay so far, which is what is expected by the question. If everything is okay, everything is balanced, for every opening there is a closing, for every closing there's an opening, then we have to print okay so far. So we elegantly use this else clause of the for loop. This else clause belongs to the for loop. And to print this okay so far. It's only executed when the for loop finishes properly without the break. And that's the first example of problem solving with a stack. So I would say this is a fairly traditional or classical question, like using a stack to check that something is balanced in this form. Yeah. Okay, and unfortunately I cannot see the questions, but let me look at the time. So it's about 8 o'clock, so we have half an hour. I think that's probably just about right, because we have one more question to go through, which is also using a stack, but this time it's much less obvious that it's going to be using a stack, but I've already said this is stack example number 2, so it's going to use a stack somehow. Let's look at the question first. For that, I'll go to the website. Here, yeah, perhaps you could read the question a little bit, because I think it's important to understand the question. So here, let me just give a context as you read. So we are assuming that somehow your computer got hacked and someone installed a keylogger. Right? A keylogger is something that tracks every single character that is pressed on your keyboard. Right? And normally a keylogger is used by malicious people to try to catch you when you're typing in your password, right? Because you typed it on your keyboard, and because the keylogger tracks everything, it would also track when you're typing your password. And when they have the password, they can use it to log in as you, pretend to be you, and do all kinds of bad things, right? So that's obviously not good. But ignoring the bad things, this question is about trying to figure out what is the word that somebody has typed, right? Because when you type, sometimes you make mistakes and then you press backspace, right, to delete the mistake. Or you might press left and right cursor keys to move along the thing you've typed, to insert a character somewhere and so on, right? Because there's always this cursor which tells you whatever, when you type, where does it appear, and you can press left and right and so on your keyboard to move the cursor to insert a character, not at the end, but somewhere in the middle of your word, right? Because maybe you forgot to type the letter, you could press left, and then you add back in the letter at the place where you forgot, right? And similarly, after you press left, you might want to press right again to get back to the end of the whatever you were typing, right? So these are the only kinds of characters we would consider. Either it is going to be lowercase, I don't know if you can see this, lowercase letters and numbers, which are basically which will appear wherever the cursor is, right? So these are just a normal typing, right? Lowercase letters and numbers. And sometimes it would be the left arrow key, the right arrow key, or the backspace, and they all operate as you might imagine. But for representation in this task, they are represented by capital letters. So these capital letters, L, capital R, capital B, don't represent you pressing capital L. It means, capital L means you are pressing the left arrow key, capital R means you're pressing the right arrow key, capital B means you're pressing the backspace key, right? These are sort of representing other keys. That's why in the actual letters are going to be lowercase, so there's no confusion, right? There's no capital letters in whatever this person, Benny, is typing. And furthermore, it tells you some simplifying assumptions. So for example, you don't backspace when you're right at the beginning, right? So, and similarly, this person doesn't press L when you're right at the beginning. Technically you could, but you'll see why this is a helpful assumption, right? So we assume that at the very beginning, you don't B or you don't press L when you're already at the very front. And similarly, you don't press R, you don't keep pressing R when your cursor is already at the very back. Right. So this is quite helpful actually. And there's some restrictions about the size and so on. Oh, so if you see, let me just quickly give you a pointer here. I think we have a bit of time. So if you see these kind of things in a question, you probably have to realize that how efficient your program has to be to successfully gain these points. So if you see, so it actually gives you various simplifications of the problem. So in the first set of 10 points, there are no L, R, or B. Oh, sorry, by the way, I forgot to say, the output of the question is what was the actual word that is typed out. that is in lowercase and numbers without all the L's and B's and all whatever. So we assume we simulate all the typing, right? When you do L, the cursor moves. When you press B, the character gets deleted and so on. We simulate everything. At the end, we will figure out what is the actual word that is typed out, right? So that's the output. So we're just simulating the action of L, R, and B, plus, of course, the actual typing of the lowercase and numbers. So the first subtask, we would say, is that neither L, R, or B are in the string. That makes life a lot easier, I think, right? So if you think about it. So if there's no, this person never presses left arrow, right arrow, or backspace. He only presses lowercase letters and numbers. So as you can imagine, that means the output will be exactly what is the input. You just have to output the input, and then that's 10 points, right? Because if you never press any L, R, or B, then it is literally whatever you type will be whatever you would appear, right? Because you never move the cursor, right? So you always add characters to the back. Then it's just exactly whatever is in the input. So that's 10 points just for printing out the input. Then you might see a next bunch of points when there's no restrictions, anything can appear, but the number of characters is relatively small, like about 1,000, right? So about 1,000, then you can imagine if you have something that does an order of operations n square, that could run in time, right? If you require n square operations, n square is about 1,000,000, right? So 1,000,000 operations could possibly run in time, even on Python, which C Python runs a little bit slowly. So if you don't have a very efficient implementation, if you use a plain list to do, for example, if you use a single list to represent this buffer of what is being typed, and then as you move left and right, you move around the list, right? And as you type letters, you append into the list and so forth. This would result in this kind of complexity, right? As we saw, because appending to the list, and which is typing in the middle, or pressing backspace, which is deleting from the list in the middle or near the front, is going to be very slow. So if the question keeps deleting from the front, right, and so forth, and if you use a list, then it's going to be every deletion is going to be order n, this linear line, right? This linear graph we saw. Every deletion is order n. So we do n deletions. So that's n times n. So that's order of n square, right? So that's roughly, on the order of 1,000,000 operations. Because of all the compaction of the list that must occur, right? As we delete from the front, we must move everything up front and so on. So, but it will be able to get this second group of 13 points if you use a single list, which is the sort of the straightforward way of doing this. I wouldn't go through the details because there's not much time. So I think the point here is to say that if we use a single list, it's not going to get all the points because of these problems, right? Because deleting from the front of the list is going to be, or deleting from the middle and all that's going to be slow. So we need everything to be fast in order to clear all the 5 groups of tasks, which is n up to 1,000,000 characters. So if you think about n is 1,000,000, then n square, which is 1,000,000 times 1,000,000 is a huge number, which is definitely not going to finish in time, which is they only give you 1 second of CPU time to solve this. So very little time. So it's not going to be able to do 1,000,000 times 1,000,000 operations. That's some gigantic number which you cannot finish in time. And so if there's such a large n, then we might want to think about, probably we need to do this in kind of close to about 1,000,000, or maybe 2 or 3 million is probably fine, but not like 1,000,000 times 1,000,000. That's too much. Right? So every operation, every character has to be processed with just a few steps. Right? So every operation, N, L, capital L, capital R, B, and so forth, should ideally be done with just a couple of steps of Python. Definitely not like the delete and the pop, where you have to do lots of compaction. Right? Okay, so let's look at okay, I think we're just about on time. So let's look at the solution. So one list will not work. And actually, what's the problem with the list? The list is problematic because we only can operate on the back. Operating on the back of the list is fast, but not in the middle or not at the front. So if the back is fast, then maybe we just need to put 2 lists back to back. Well, but not 2 lists, but 2 stacks actually, right? Because we only care about the back or the top. in this case. So here we'll consider this particular construction, which is two stacks where the top face each other, right? And the interpretation is that the middle of in between the two stacks is actually where the cursor is, right? The cursor is where you type, where new characters appear. So let's suppose we're given this sequence, A, B, E, N, so on and so on. How does that look like when we try to simulate this? Right? So we have two stacks. One is called the left stack and one is called the right stack, and it will be obvious why later. So as we type, we are adding to the left, right? Because the cursor always goes behind whatever we typed. So as we just type stuff, it just appears, we just essentially append it to the left stack, right? Because the cursor always goes after what we type. Now when we press L, next character is going to be capital L, which is moving the cursor to the left. What happens? Nothing gets deleted, right? So moving the cursor to the left means the cursor is now going to be between O and I, the last two characters, right? That's moving it one step to the left. How would that happen? Well, we just have to pop from the left stack and move it to the right stack. Right? Then we have the cursor precisely between the O and the I as expected when you move it to the left one step. Then we continue typing. We type N, which just goes in between. So become B-O-N-I, right? And then in the sequence, there's a whole bunch of L's. L, 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 L means left, 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 left. And we do the same as before. So we are, essentially, if you think about it, the cursor actually, what happens is actually quite weird. The cursor actually never moves, right? What is moving is the characters, right? But normally, if you look at the actual application where you do typing, the cursor is moving. But here in our simulation, the cursor is sort of fixed. And we are moving the characters around to simulate the cursor moving. But it achieves the same effect, actually. Okay, so after a whole bunch of L's, I think we get to this point. So the cursor is just after the A, right? And then what happens? Then this person presses backspace. So backspace is quite easy. Backspace means we delete whatever is on the left of the cursor, which is the top of the left stack. So that gets deleted. And here it's guaranteed that the person could never press L or backspace in the question, so we don't have to worry about that. The next bunch of characters pressed is a bunch of right arrow keys, R, 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 R. That doesn't do very much, but it just reverses the left, which is move the characters, right? So the trick is we always move characters, we don't move the cursor. The cursor is kind of fixed. So we just move the characters in lieu of moving the cursor, but everything is relative, so it's essentially the same result. So we move the characters backwards. So now they go back onto the left, or from the right to the left. And then a bunch of backspace happen. And again, backspace here means we're deleting whatever is to the left. So O is gone, and then B is gone, right? So at the end of the day, we just have to print out whatever is in the stacks, which this case would be B, E, N, and I. And that would be the result. I believe this is one of the input cases. So let me just run through the three cases again. So if it's just here, the trick is we're moving the characters, not the cursor. When it's just a character, we always add it to the left because the character is always typed on the left of the cursor. L means we are supposed to move the cursor, but because that's kind of tricky, we're going to move the character. We're going to rearrange the two stacks instead. So L means we shift a character from the left of the stack to the right of the stack, right? This one, which is similar to moving a cursor to the left, right? N is as usual, and then all the L's. Backspace is removing what's on the left of the cursor, which is easy because it's just the top of the left stack. Right is shifting the stuff the other way around from the right to the left, which simulates moving the cursor to the right, but actually the cursor doesn't move. The characters do. And backspace I explained before. Okay, so that's a recap of the whole sequence. So let's see the Python code. And actually, this looks a lot nicer. Actually, I prefer this question because there's no space for one thing to mess things up. There's no spaces. There's always either the lowercase letters or numbers and the capital L, R, and B. Okay, so at the beginning, we have to set up our two stacks, which we'll use lists because lists operate well on one side. So we'll call them left and right for obvious reasons. Then we go through every character in the given sequence of the keylogger. Here we also don't need the enumerate because we don't really care about the position like we do just now. So we just, for C in sequence, it's sufficient. Then we have to handle each of the 4 cases, right? There are 4 cases to consider. So first case here is if C is the character L, capital L, which means pressing the left arrow key, and it just shuffles, it pops from the left stack and appends to the right stack. R is done in the same way, except the other way around. And B, as you saw, is just popping whatever is on the top of the left stack. So left dot pop. And finally, if it's not neither of these 3 things, it must be either a lowercase letter or number. Then it's just going to appear immediately to the left of the cursor, means appending to the top of the left stack. All right. And at the very end, then we have to do a bit of small data juggling just to get it into the right sequence. So at the end, I think if you look at the list on the right, the front of the list is actually I, right? Because the back of the list is the top of the stack, as you recall. So the list is actually sort of the wrong way around. The left stack, aka list, is fine because the front of the list, the left list is B, right? So if you just print the list, it's going to be BEN, that's correct. But the right list is kind of the wrong way around. So we got to reverse the right list. So we do a right dot reverse, which flips it over. So it's now correct. And then we just print all the characters joined together. Here we are joining with the empty string, means there's no separator, right? So it's just going to create one giant string with all the characters from the left and the right. And recall that the right has been reversed, so it comes out correctly. And we just print, in this case, the password. And that would be the answer. Okay, and that would be this second question. So let me just do a quick recap. I think I have a bit of time. So let me just recap to here, maybe, or maybe even to the question. So the key idea, I mean, our restriction really, because n is such a large number, up to 1 million characters, we have to do every operation in just a few steps. We can't iterate over things and so on. So if you notice in this particular solution, that's exactly what happens, right? So every operation is really just a couple of steps. In more traditional languages, you might encounter a different data structure called a linked list, which also can be used to solve this problem. Unfortunately, Python does not have linked lists at all. So, well, you could obviously implement one yourself, but that's quite a lot of effort. But if we want to make do with whatever Python has, this is kind of the closest we can get, right? Because by joining 2 stacks or 2 lists, the back-to-back together, right? We are able to only perform operations at the back. And that's the key, right? We're only performing operations at the back or at the top of the stack where things are fast. We're never doing things at the front of the list or in the middle of the list, or in the middle of the list where things are slow, right? It's still one operation, kind of, it's still calling pop, right? But as we saw from the very early hands-on, calling pop in different places, for example, can involve different magnitude of work. If you call pop from the very back, it's really fast because it's just getting rid of the element and there's no compaction. If you're calling pop at the very front, pop bracket 0, that is actually very slow because that's got to compact all the things forward 1 step, right, to cover up the gap from the deletion of the thing in front. So it's important to know about the specifics of the operations, like for example, in this case, pop, right? So pop is only good or mostly efficient when it's at the very back, but not at the front. Okay, I think we have some time for questions that I can answer on stream. But in this case, we can do the feedback. So there is a URL where you can get a recording of this video. We will upload it later after the session. And that's for the left. And